in class we have a test. So it's our optics test. And as I mentioned last Thursday was our last optics one. I just went as quickly as we could. I wish I had a time to do more examples. I know Don did a bunch of really good examples on Sunday, and so hopefully the review, oh, that's not your review, that's this Sunday, another class. But anyways, hopefully that went well for you. And now let's move in to the next unit. Yeah.
Did you want us to try to finish chapter 30 at home?
Chapter what?
Chapter 38 homework?
I would put it this way, whatever works best for you. If you finish all of 38, I think that makes the most sense in the sense that you're going to have a test on it on Thursday.
On the material we didn't cover in class.
But, maybe I didn't let you finish your question. On the stuff we didn't cover in class, you don't need to do.
Okay.
Yeah, so, but that was, maybe I should go look at the homework. Was there stuff on polarization by, say, scattering? Okay, because we actually got, like I said, at the end of class, much further than I really anticipated, given we were behind. The thing that really hurt was we didn't get a chance to do many example problems. That was the unfortunate part. And unfortunate when I'm bothering to videotape this one, so it'll be up there for years and years and years, and there won't be any examples from that chapter, or those two chapters. But should have videotaped Don's on Sunday there. I thought you were asking it slightly different. I would encourage you to get the homework done before the test. However, studying for the test is certainly far more important first. So, in a perfect world, you would, of course, have read it. You would have done the homework. That would have been all behind you by now. And now you're studying for the test, and you're ready to turn in the homework in there. And this time of the semester, I know that things can get really hectic and really busy, and I know you have, you're coming to the end where things kind of get jammed in together, and you probably hit the most difficult stuff in your math, the most difficult stuff in your physics, the most difficult stuff in your engineering, and all those term papers in English 110 you thought you would have more time to do, you put off till the end, and those big computer programs you thought, oh, you'll have more time near the end, and all of a sudden we're at the end and it all kind of comes together here. So, yeah, but if there's any that are on, if there's anything that's beyond that polarization by selected absorption, which is what we did with the polar issues, yeah, don't do that. And I'll if you got a question, ask me, but I'll look at the homework assignment. All right, so with all that said, let's shift gears today, and let's begin our introduction to the 20th century. Here we go. We're finally going to hit 1900 here, 1905 to be particular, and look at some of the work done by Einstein. And for some of you, this might be quite interesting and quite surprising. Well, others of you have been exposed to it, so it won't be quite as bizarre. But you might hear that word a few times today, and as we read the chapter, and your attention probably going to be more focused on getting your optics test done. So the next Tuesday when we come back, you'll still hear a lot of, well, that's bizarre, or that can't possibly be true, or I've heard students say this, well, I don't understand it, but just learn it because it's on the test. It's not right, but it's on the test. and hopefully it doesn't come across that way to you. But there is some very interesting phenomenon that is going to take place here as we get into chapters 39, 40, 41 and 42, and just however far we get. You can see why we put it in its own little category. It's called modern physics. A lot of interesting discoveries that happened in what we often call the 30 years that shocked physics, 1900 to 1930. Just some weird discoveries that didn't seem to make a lot of intuitional sense. And the best answer I can give you is because what we're going to be talking about is either things going very, very fast, and things just are different when you go very, very fast. There's no reason why they need to be the same as what we're used to, but that's why it bothers us, because it doesn't act like what we're used to. Things are different at these speeds, and we're not used to it because we've never gone close to the speed of light, at least we individually. And so that the world at close to the speed of light does have some bizarre effects, and it's not going to fit right with your gut intuition. And the other side of this is going to be the really small things. We're going to look at things as the size of the atom and smaller, and we're going to see, that doesn't seem quite right either. But again, it's going to be my same answer. It's going to bother you a little bit. After a little while, it'll kind of hopefully sink in and make you feel a little bit better the longer you work with it. But again, you've never been as small as an atom, and so what goes on inside of the atom could be different and could be a little bit more bizarre here than what we've been used to for the last 3 semesters here. So I'd like to say here as we get started is chapter 39 is the first chapter on this section, which we refer to then as modern physics. And this first one was discovered by Einstein. He called it relativity. And what we really mean here is he's going to look at relative speeds. What does something look like relative to another? And so one may be moving, one may not be moving, or maybe they are both moving. And so hence the name relativity. Maybe more importantly, we should call this special relativity here. Because what he's going to say is, let's look at the simplest case where accelerations are 0. So in other words, if we have something that is moving relative to another, that's fine. It just continues to move at that same speed in that same direction. Because no doubt, the next question is, well, what if the speed was changing? All right, well, that was Einstein's next question too, which, by the way, he figured this out in 1905. Figured out ones with acceleration, which we now call general relativity, 10 years later. So there's a big step between trying to understand what we'll do now and what if you have accelerations. And that's not our intent here. Our intent is to get it just without acceleration. And if your education takes you to the next step, the next level, where you do general relativity and special relativity, then you'll make that next step. That's what, a lot of our optics and our thermodynamics were all about. They weren't a complete course in thermodynamics. They were a good 4 chapters, and we got into some good stuff, and they're going to get you ready for the next level. Same thing we can say here about optics, and the same thing we can say here about modern physics. But I do want to throw out some terminology here. This, up until this chapter, and so really for 3 semesters, although some of you haven't done Physics 122 yet, and you're going to do that in the fall. All right, but this whole book, the first 38 chapters, are things all discovered before 1900. We refer to this as classical physics, or sometimes Newtonian physics. It's centered around Newton's 3 laws of motion, which we got started with way back in chapter 5. Maybe a little more credit is you'll hear it called Newtonian Galilean physics, so that we can give some credit to Galileo and the work he did. All right. And in fact, that's probably the best way to get started. The best way to get started is say, what if we take something really small? And so let's take an electron. Now, not so much because it's an electron, but because it's small, it won't be hard to get that object to get going really, really fast here. And so this whole lesson kind of begins, and this whole discovery kind of begins in the late 1800s, where the early scientists did something like this. They said, let's take an electron, which is negatively charged, and off to the side, let's put a positive plate. So we'll take a metal plate and we'll make it positive. Now here's where I have to pause. Some of you have not done Physics 122 quite yet. That's okay. I'm not going to do too much in the physics 122. You might say those of you who went 122, maybe this would mean a little bit more to you. But I just want to check that even if you haven't gone through physics 122, what do you know about a negative and a positive object? They attract each other, right? And so this was the early experiment. The early experiment was simply, let's take an electron, let's take a plate, and what will happen is if you let it go, it will then go faster and faster and faster and faster, right? And so if you charge up this plate to a few volts, maybe about 10 volts, maybe I should pause right there. Again, many of you haven't done 122 yet, but at least half of you had. Again, not going to be worried too much about the equations here. That's not the intent. The intent is just to say, what do you think would happen between the difference of 10 volts and 20 volts? Right, I would put more charge on there, and more charge means it would grab or pull that electron with more force, and it would make that electron go a little bit faster. Fair enough? All right. So they do 10 volts, they do 20 volts, they do 100 volts. As technology develops, they get to 200,000 volts. Now, with 200,000 volts, that is a lot of work on this little electron. Now, again, many of you haven't gone through 122 yet, but you have done the work energy theorem back in chapter 7. If you do work on an object, that equals the change in kinetic energy. If we start from rest, we can throw that one away and figure out what the final speed is. Now, the work part is actually the charge of this electron times the voltage. Now, again, I'm not going to really do any calculations. I just kind of want to prime the pump, so to speak. I just want you to kind of see some of these early experiments, because you got to understand what's going on. What's about to happen and what's about to be discovered is not something somebody just logically worked out. It's like, hey, you go to the experiment and something weird happens, and now you have to explain why. And you might have to change your whole thinking, and that's what this chapter is all about, to kind of plant that seed that our thinking is just not complete. Right? And here's the first experiment that shows it. So again, not worrying about this product, I just wanted to say, though, that if you do take the charge of the electron, for those of you who know the charge of the electron, and you do charge up this plate to 200,000 volts, and you put those numbers in there, and you put the mass of the electron in there, you get a final speed that is about 88% the speed of light. Now, let me pause right there. Notice I just didn't give a straight number. I gave it in a percentage of the speed of light. So I'm going to use C, now that we've done our optics, for the speed of light. And I think you know that number. What's the speed of light? Right. So if you really wanted to do this calculation, you are more than welcome. This would be how fast it's going to go. All right? And obviously a big number. And not really a surprise yet. But here was the neat thing. Once technology got this far, scientists realized, hey, 10 volts makes it go somewhat of a speed. 20, twice as much voltage would be twice as much work. 100, well, that's a lot more voltage, a lot more work, a lot more speed. 200,000, wow, we can start to get close to the speed of light. So what would it take to go more than the speed of light? Let's try that. And so early scientists said, well, if we can get 400,000 volts, maybe we could do, 200,000, maybe we can get 400,000. And so one of the first experiments that you'll see here is a little bizarre, and really at this point unexplained, is if you charge this plate up to 400,000 volts, and you apply Newtonian physics here, classical physics, all the stuff that you learned, and you say, all right, let's calculate the work, and you put then the charge of the electron, you put the 400,000 volts, you put the mass of the electron, Oh, well, I said I wasn't going to do any calculation, but now oh, bummer, I did. All right, so those of you who might remember some of these numbers. Ah, yeah, okay. So, yeah, there's the famous 9/11. All right, good. You guys remembered it from fall. Oh, don't give it away for the rest of them. It's got to be a surprise. Yeah, special number in September. We'll see. Okay, but there's the charge. There's, anyways, you would get V squared. Now, if you do all this math, you get 125% the speed of light. And you can imagine that scientists probably at this time got real excited, say, hey, we're going to make something go faster than the speed of light. We're going to charge up this plate. We finally have found things that are small. We have finally found technology that gives us enough voltage. We can finally make something go faster than the speed of light. Let's try it. And then they measure its speed. Guess what they get? They don't get this. They don't even get close to that. Well, unless you call 96% the speed of light close. But they didn't get faster than the speed of light. And I'll kind of leave that alone, but you can imagine their thought process. Something to the effect of, oh, well, we don't have enough voltage, or we did our calculation wrong, or maybe, as you guys would say, my partner messed up. And it really was going faster than the speed of light. We just took a poor measurement here. But no, again and again, the experiment was done. 400,000, 500,000, 600,000. And so, no matter what the voltage was, there seemed to be a pattern.
How in the world do you get 600 lightning bolts above making a lightning arc?
You keep everything else, away from it. No air. It's 600,000 is not too unreasonable. It's not easy. You're right. Which, but not too unreasonable. All right. So, anyways, but some of you already mentioned it. Never went faster than the speed of light. Keep that in mind, because that's an important idea here. And in fact, all this was going on, and I love this quote by Einstein. He says, there is just something really wrong. There is a deep contradiction in the old, and when he says old, what he means is Newtonian, in Newton's theory, ... And so this may be for some of you the first time. It's certainly the first time I've said it to you, but we just did 38 chapters that are, I don't want to say wrong, and I don't want to say worthless, but I do want to say incomplete. It's not the whole story. And in no way is it obsolete. In fact, you'll begin to see the different direction that the engineers versus the scientists will start heading. Because notice here that this becomes more about science than it does about engineering. Because when you effect, as we get close to the speed of light. So how many cars go close to the speed of light? How many spaceships go close? How many trains? How many? It's very seldom we have things going close to the speed of light, or at time accuracy that is needed on that time scale. You mentioned it earlier, the GPS system. So yes, there is some engineering that does have to take this into consideration. And it's that engineering where the engineers need to take one step further, and they need to go beyond Newtonian physics. But I don't want to say that your F equals ma is in any way incomplete. Well, that it's wrong and obsolete. You might say it's incomplete, and if you ever find yourself in a situation where you're designing a spaceship that's supposed to go 90% the speed of light, certainly do not use F equals ma. That's where I'll get started here. You will hopefully get a pink slip right away and say, you were an okay student and you got an okay grade, but you need to work someplace else, okay? No, but but this is kind of that next step. And so, if you're designing levers and gears for doors and DVD players that open and close and hard drives that spin around, F equals ma is absolutely fine. Do not get rid of it. It is so much easier than the math you're about to see that we still want to do it that way.
Can they use it for missile defense?
No, you could still do absolutely fine on missile defenses, because the missiles themselves, the kinetic energies of them are not even close to the speed of light. Now, you might say the light itself goes the speed of light, but that's fine. We've got our classical optics that you're about to have a test on. That doesn't change much. Well, the light goes the speed of light. And that's how we've treated our optics. So none of our classical optics would change. So the answer here is there's got to be more here. We're missing something here. And you'll see that here before this chapter is over. I'm not sure today, but next Tuesday we will re-look at F equals ma. We will re-look at the formula for kinetic energy. We will re-look at the formula for momentum. And the good and the bad news is, good news is we will discover some really neat different things. But we'll also learn that we've got to redo everything, because what we've learned so far is incomplete. So we will go back and start redoing our mechanics. Well, let me keep going here, because again, just to kind of get you interested in the topic and what's going on, this is kind of the first sets of experiments that were done that just didn't make sense. If you continue to use, and if you remember, this equation came from F equals ma. We integrated this. We integrated the work in Newton's second law to get this equation. And it doesn't seem to be working. It seemed to work fine when we were pretty slow. And when I say pretty slow, I mean less than 10% the speed of light. Which, by the way, what would be the value of 10% the speed of light? 3 times 10 to the 7th meters per second. It's huge, right? It's over 18,000 miles in 1 second. All right, so as long as we are willing to go less than 18,000 miles a second, we can continue to use what we will refer to then as the old theory, the classical theory, the Newtonian theory. We don't have to take this next step. Well, let's look at another fun experiment, because it ties in with our optics, the stuff we just got done with here. And you probably remember, I would assume quite remember it, given that you just did a lab on it and given that you are probably reviewing heavily for a test in 2 days, but the Michelson interferometer. As I mentioned, I wanted to talk about it in detail in class in our optics, because Michelson, is actually Michelson and Morey, had a great idea. They said, let's use this interferometer. Yeah?
Supposed to get to 10%, does it get progressively less accurate, or is that 10% that we just like?
It's a continuous function, so it progressively gets, and it's exponentially, if you will. We'll derive it here in a minute. So at 10% the speed of light, our equations are 0.5% off, as you'll see. So they're not even that much off at 10% the speed of light. But by the time we get to 90% of the speed of light, they're off by a lot. I'll forget the number, we can calculate it here, but it's off by a lot. So, and so it's a progressive change. Yeah. But if I draw the Michelson interferometer up here, and even show you a picture here of it on our animation, it looked something like this. Let me put the 50% mirror right here and say, okay, here comes the beam of light. As you probably recall, there would be a mirror at the top and a mirror at the right. And what we went through was it would bounce off there, and it would bounce off there and come together. And if we put our screen down here, we may get constructive or destructive interference, right? And our logic being that, well, you got to look at the path difference between those two. How far does it take to go from one to another? And it was Michelson and Morey that had a great idea. They said, what if we, actually, I should show it here first. Let me just go to our flash page. But Michelson and Morey said, what if you take a beam of light and you send it to that mirror, then you send it to this mirror and back? All right. So let's just say we do that. And for the sake of conversation, let's just say we adjust it so that the distance from here to here and the distance from here to here is the same. And that's what's kind of illustrated in this picture. And so if I hit play here, they said the light would go out and meet back up here at the same time. Right? Now, of course, if there was a distance relative to this one and this one, then you would get a dark spot or a bright spot. And that's how you learned the interferometer. You learned the interferometer by saying, let's just take this path and let one of the mirrors move. And if you let one of the mirrors move, we would go from constructive interference to destructive to constructive to destructive. Fair enough? But they realized this. What if the interferometer was in motion? And they thought they had a brilliant idea. And this is somewhere in the late 1800s. And they go, we've always wondered how fast the Earth is moving. Isn't this a great experiment to show it? And here was their logic here. Their logic was, if you have this interferometer, and this interferometer is sitting on the Earth, then as the Earth moves, let's just say the Earth is moving this way, then what would happen is the light would go out and it would try to catch this mirror and bounce off, and if it came back, this would have moved over to here, and you would get a ricochet. Fair enough? But likewise, if the Earth is moving, as it moves along, this beam's going to go up and hit the mirror. And so this mirror would have moved over by then, and then come back down. And I think this explanation helped show it. Maybe you could see their logic. Their logic was, okay, what if we have an interferometer that is moving? See, because it is moving, we would have to analyze it a little bit different. And let me not take the time to analyze it, but I'm hoping you would see that the light that came here would have to go up, and as you saw, it hit the mirror, and then it came down here. Versus the light that went out to here, and it hit this mirror maybe right about there, and then went back down. Let's see it again. But the most important thing to realize is they don't meet up back at the same time, do they? And so by the time they do meet up here, you would have to travel an extra distance. And so they realized that an interferometer in motion is kind of like an interferometer where you're moving the mirror back and forth. And with the fringes in place, they said, hey, I got a brilliant idea. We wanted to always know what speed the Earth is moving. This interferometer that is sitting in our laboratory is sending the light out. The Earth is moving. And so we will send it out, we will ricochet it back, and of course when we first set it up, we don't really know what direction the Earth is moving in this big universe of ours. And we know that we will get some kind of pattern, but their logic was that if you set it up, so my arms will be the interferometer arms, and you set it up, then if you just rotated the interferometer 90 degrees, then somewhere in that rotation of 90 degrees, one mirror is going to go from moving in the direction of the Earth to 90 degrees. And the point is, you would go from this mirror hitting first to when you rotate it, this mirror hitting first. And as you were rotating it then, because the path difference would be changing, shouldn't there be fringes and shouldn't it go bright, dark, bright, dark? And so their brilliant thought was, if we take this and rotate it 90 degrees, although it's pretty complicated, we rotate it 90 degrees, we should count the fringes. And as we count the fringes, we will know the difference between when we were going with the direction of the motion of the Earth and perpendicular to the direction of the Earth. And how many fringes there would be based upon how fast this interferometer is going. It would be based on how fast the Earth was going. And so I'm sure they were very excited and going, we're going to get it. We're going to figure out how fast the Earth is moving. So they tried it. You know what they got? 0. Yep. They were real careful. They put it on there. If I remember the numbers right, I think the arms on this interferometer were like 26 feet. And they rotated it, looking carefully at the center. Is it bright? Rotate it. Still bright? Uh-oh. Rotate. Still bright? Uh-oh. Still bright? Uh-oh. Still bright? And they rotate it 90 degrees. I'm sure they tried it many times. I'm sure they blamed it on their partner too. And said, and they had no explanation. Unless you'd say the Earth's not moving.
It is the center of the universe, right?
But they knew it was at least this much, that the Earth does go around the sun. So they even thought, maybe we just happened to do it at the moment when the Earth wasn't moving. Maybe something like this. Maybe here's the sun and the Earth is going around like this, okay? And so right now the Earth is going that way, but at the same time the whole galaxy's going this way, plus the spin. Maybe that just happened to come out to be 0. I mean, maybe it was just really bad luck. But 6 months later, we should be going with the direction. So let's just wait 6 months and do it again. So they waited 6 months, they did it again. Guess what they got? 0. And I don't know how many times they ultimately did it, but they kept getting 0, 0, 0. So today, we call this experiment, believe it or not, one of the most important experiments ever done. Interesting enough that they got no results. So we call it the most famous null results. Because they could not explain it. I, at this point, can't explain it to you. We know the Earth wasn't stationary, but within 20 years, Einstein will put this together and come up with his theory on special relativity and explain why the results should come out to be nothing and should be a surprise here. And so, as we come back and look at this a little carefully, and we begin to analyze this, here's kind of our first approach. Einstein looks at this, and the reason I picked these two experiments was to kind of get us started and say, there's something about the speed of light. There's something magical. There's something more going on than the speed of light. Many of you have already asked that question earlier on. Do radio waves travel the speed of light? Mm-hmm. You asked a little while ago, do gravitational waves travel the speed of light? Mm-hmm. And it's too bad that we call it, even to this day, the speed of light. The truth is, there is something magical about that speed. It is the ultimate speed of the universe. We should probably call it the fundamental speed of the universe, or the speed limit of the universe. There are lots of things that go the speed of light or less than the speed of light. Nothing goes more than the speed of light. And it's too bad we use the word speed of light, because that implies, only light. No. It's just light is the first thing humans discovered that go the speed of light. But there seems to be something far more important about this number than just, hey, this is the speed that light goes. There's something more important in the universe here. And as you'll see in a minute, this is the way Einstein began to think about it. He said, you know what? There is something interesting about the speed of light. And as you'll see in a few moments, his first work was to say, Well, what if the light always travels the speed of light? Regardless of whether the interferometer was moving or not. You see, if it went the speed of light, then this would go out and travel the speed of light. This would go out and travel the speed of light. It wouldn't be the speed of light plus the motion of the Earth. Let's see if this begins to make sense. Here's kind of the first work. Here's where Einstein gets started. He says, all right, let's look at this question. And of course, Einstein thought a lot about trains, partly because in his day that was basically the mode of transportation, and partly because his office sat over a switch yard, a train switching yard. So he had all these trains to look at. So don't be surprised if all the examples that the book talks about and I talk about have to do with these trains. But whether it's a train or any other object, let's do this for a moment. Let's say that I am in the train and you are outside of the train watching me. Okay? And so I take an object, such as this pen, and I am traveling in my train. So I'm going along in the train, and let's just say the train is traveling at 4 meters per second. Okay, not real fast, just kind of moving along. All right? And so I'm moving across, you're watching me, and I take an object and I toss it up. Now I know gravity slows it down, but forgetting gravity, let's just say I throw it up. I throw it up with a constant speed, and I throw it up with a speed of 3 meters per second. Now, from my perspective, and here's where the word relativity comes in here, what do I say the speed of the pen is? 3, right? Straight up, right? And so as I look at it, I being inside the train, and so I will say inside right here, okay, me, I would say the speed is 3 meters per second. I'll even say up. But what would you see? So the person on the outside, as some of you already did, would say, well, it would probably look a little bit like that, right? I mean, you got that because you said, well, there would be the horizontal motion of the train before. Then you would combine that with the vertical motion of the 3. And the total speed, and I heard some of you say it, is what? 5. And how'd you get the 5? Oh, you use Pythagorean theorem? Right? They're 2 vectors and you add them together. So you did something like this. You said, all right, the total speed, I'll just put speed total, is really the horizontal speed plus the vertical speed, and you squared it, right? And so in this case, you took a 4 squared, a 3 squared, and you came up with a 5 squared. Why?
That's what we see.
Why does the Pythagorean theorem work this way?
Because that's the magnitude of those 2 vectors.
Let's see if we can kind of answer that question a little deeper. Because this is really the key to Einstein's brilliance right here. He looked at this and said, well, why do we do that? Why do we take the horizontal speed and we square it, and we add it to the vertical speed and we square it? Well, why do we do that? What makes us think that that's even right? We seem to have doing it for hundreds of years. But why do we think it's right? What is our justification?
Position helps you along it.
All right, let's do this for a moment. Now, this one's not much better. I'm looking for a little darker one here. Let's call that angle theta here. Let's do a little bit more work here. Let's analyze it, as I said, like Einstein's about to do here. Einstein said, okay, let's take a look from the outside person here for a moment. That outside person being you. And said, well, look, if you just watch it go up, and we'll watch it go up, and say, let's just say the height is h. Okay, you, being the outside person, would have done this. You would have said, okay, let me take the speed that you see. You're the outside person. Let me multiply that by the sine of theta. Okay? So, if I take the speed that you see, right, and then you multiply by sine theta, right, that is your vertical speed. Fair enough? Then if you multiply that by the time that you, the outside person, is going to measure, wouldn't that give me my h? Right? All right. So again, hopefully anything I'm doing here isn't too new to you, but it is going to hopefully answer this question. Why do we do this? What is our justification for doing this? And it might be a little surprising. Now, let me look at the inside person for a second. The inside person, well, that's me, would say, okay, what do I see from the inside? And of course, from the inside, I just threw it straight up. So there's no sine or cosine of anything. Okay. Then I multiply it by the time that I measure on my watch on the inside. And I say that is equal to h. Fair enough? Now, if I do a little bit of work here and say, all right, we both agree, outside and inside person, that they go up a height h. I guess where we're kind of questioning here is this velocity thing. So let's do a little bit of math. Let me take the velocity of this outside person. And I'll even just change the order here. Time from the outside person. Sine theta. And I'm going to set it equal to the velocity of the inside person multiplied by the time of the inside person. In fact, you kind of begin to see it right here. That what did you do, and what have you been doing, and what had humans been doing for 300-400 years before Einstein, is how did you get the vertical speed? Didn't you take the outside speed and multiply by sine of the angle? And you can see it here. Isn't that true? Only if the time measured by the inside person is the same as the outside person? Oh yeah, but it's got to be, right? Let's keep going with this. Let me change this a little bit. I'll do a quick trig identity that will become very useful. I'm going to write this as the square root of 1 minus cosine squared theta. All right, velocity of inside, time of the inside person. Okay, so then I got this square root. Let me get rid of the square root by squaring both sides. Okay, so this is going to be velocity of the outside person squared, time as measured by the outside person squared, 1 minus cosine squared theta. This then equals velocity of the inside times the time of the inside. Now I picked this one because the cosine is going to be a little nicer to work with than the sine. That's why we did our little trig identity. In fact, let's look at cosine of the angle. What would you define as cosine of the angle? Well, I guess I would call it the velocity in the x direction. This would be the velocity of the train. And I'll go velocity in the x direction squared over velocity as seen by the outside person. Okay? Equals. And let me just cancel that off for a moment. Oh! I heard somebody, is that what you guys were saying? I forgot to square that side? All right. So make sure I square both sides. And then I get what I really want you to see, and this is where Einstein's brilliance comes in. And really the beginning part of this chapter is if I write this as inside squared, time inside squared, plus velocity in the x squared, time on the outside squared. I'll pause there And just kind of ask something you probably were asking the whole time I was going along. Why did I put time for the inside and time for the outside? I mean, aren't they the same? So what if they are the same? What if the time as measured by the outside person is the time as measured by the inside person? What will this equation become? Yeah, the velocity of the outside person sees what? Well, the velocity of the inside person and the velocity squared of the horizontal motion. The inside person is the vertical motion, and the train is the horizontal motion. And maybe now you can answer this very important fundamental question. Why do we do this? What was our justification in saying that the speed as seen by the outside person is 5? We did Pythagorean theorem. What was the justification that it worked?
We're all on Earth.
The time from both observers is the same. What if the time is not the same? What if time is relative? I know that sounds weird. So that, forget it. No, that's just even a stupid question to ask, right? Forget it. Forget I even said that. Yeah. Dumb. You would argue exactly, well, wait a minute. I've been moving in a car, and that I never noticed the time was any different. Okay, fair enough. And that's probably why this equation had worked just fine as long as the times are either the same or very close to the same. But what if the time by these two observers are dramatically different? Would this be an appropriate way to get the speed? No. And so here's Einstein's argument here. He says, all right, this is what we've been doing for 300 years. What we've been doing for 300 years, like it or not, we have been assuming that the time measured by somebody inside the train and the time measured by somebody outside the train is the same. It's been an assumption. It's why this is used. And that's what I want to emphasize. We use this because we are assuming this. And it seems reasonable, doesn't it? Although, what seems reasonable at a low speed doesn't necessarily mean is true at a high speed. And so here's Einstein's question. Einstein's question is, maybe this is not true. Let's just at least ask the question. What if the time is not the same for every observer? What if time is a relative quantity? The time that you measure on your clock is different than the time I measure on my clock. What would that say? And so if the time on the outside does not equal the time on the inside, then you would not get the velocity squared would not be the vertical speed squared and the horizontal speed squared. Fair enough? The only reason it worked is because we are assuming the times are the same. Now let's go back to experiment. Go back to that Michelson-Morey experiment. Remember, part of that was the beam of light is going this way. Well, I'll put the beam of light this way, while the Earth is moving this way. When Michelson and Morey worked out their results, you know how they got the speed? What'd they do? They said the speed of light goes vertically at the speed of light, and the Earth goes horizontally at a speed Vx. They said then the total speed of the light beam would be this plus this, and that would be your total. And yet, the result they get from their experiment doesn't seem to match their calculation. So, Einstein's brilliant is saying, I don't think this works. And if this doesn't work, what does it mean? It means the time is different by different observers. And so we can't use this. And of course, if we can't use this, then what should we do? And that's his brilliance. He looks at that interferometer again and he said, well, what are you noticing about that interferometer? We noticed that there were no fringe patterns in that interferometer. So what does that tell us? Well, if we come back to this equation, the speed as seen by me appears to be the same speed as seen by you. Is that possible? Well, it is mathematically possible, but only if you're willing to accept that the time seen by me is different than the time seen by you. So let's try this. Let's try this calculation. Let's put in that first term c squared. Time is viewed by the outside person. In the next one, let me put c squared and time observed by the inside person. In the next one, let me put v, is that an x over there? For the horizontal motion. And let me put time by the outside person. And so again, can't overemphasize it. This is Einstein's brilliance. He said, for 300 years we've been doing this. For 300 years we've been assuming this. If this is true, then this must be how you add the speeds together. But if this is how you add the speeds together, we would not be getting the results from the interferometer that we do. The results we seem to get from the interferometer seem to say that the speed of light seems to be the same by no matter what person you have. So Einstein starts off and says, what if it is? Let's just make this bold assumption. What if the speed of light is the same for all observers? I don't care how fast you're going. Now I know that sounds a little weird at here first, but here's what it is saying. It is saying here is if I took a flashlight and I were to shine it that way, and the beam goes off that way, it goes the speed of light. If I now get in a spaceship and I go half the speed of light and I shine that beam forward, how fast does the beam go that way? The speed of light. And how fast does it look to you? The speed of light. And so Einstein is again trying to say here, without proof, but it's his second postulate here. He says, look, first postulate being, let's just say the laws of physics are still the same when you're moving. And the second one is, without explanation, what if the speed of light is the same? It seems to be what the experiments are telling us. And he was, like I said, smart enough to catch this and say, if this is no longer true, then the times have to be different. And so if we put the speed of light in for each of these, we should have a mathematical relationship between the time that you will see and the time that I will see. And so we won't get the same amount of time. And so as I go through the math here, and I move this over to here, I guess I'd have a c squared minus a vx squared multiplied by the time on the outside person, c squared time by the inside person. If we divide both sides by the speed of light, we get 1 minus the speed of the train divided by the speed of light multiplied by the speed as seen by the outside person must equal the speed of the time as seen by the inside person. Your author likes to write it this way: the time observed by you, the outside person, is then equal to the time observed by the inside person divided by the square root of 1 minus v squared over c squared. And so what is this really saying? Now again, without proof, but to kind of get us started here, is our first bizarre consequence here is trying to say that for hundreds of years we've been doing Pythagorean's theorem. Pythagorean theorem is only valid if the times are the same. That doesn't seem to agree with experiment, what does seem to agree with the experiment is that the speeds are the same. And I'm trying to emphasize then, if the speeds are the same, then there's no way the times could be the same. And that is new for most of you, or many of you. And this would be the mathematical relationship. In fact, to make our math look a little bit simpler, we like to call this the gamma function. And so we write the time as observed by the outside person is gamma multiplied by the time observed by the inside person. Let's take a close look at this function gamma. Obviously it has to do with speed. I will put the speed of light right here. What would this function look like? What happens when you're going really slow? Or I should even say zero speed. Yeah, and so when you are going zero speed, your function is 1. As you go faster and faster and faster, unless you get close to the speed of light, this is so small it's negligible. Fair enough? And so it is pretty much 1, 1, 1, 1, 1. When does it begin to change? Yeah, as you get close to the speed of light. And at 10% the speed of light, this factor comes out to be a 0.005. Not much of a change, but it will begin to change very quickly. And what would happen, of course, close to the speed of light, it would go up to infinity, right? And so here's what I'm trying to say. That the time that you observe and the time that I observe could be different. And as bizarre as that may sound, let me show you well, I'll just kind of even draw the picture here, but your author does a good one to say, as bizarre as this may sound, we've actually done experiments to measure it, and it does work. Yeah.
So, you can never be at the speed of light. How the equation says to, right?
Well, we can't get to the speed of light. I'm not sure that is a complete proof of it yet, but we're going to see we can't get to the speed of light. Yeah.
I read that the math still works if you were already going faster than the speed of light, that it wouldn't be a problem. But it was just crossing the border that was the issue.
Well, we don't know. I mean, we have some great equations that match our experiments to the t for anything less than the speed of light. We know that. If we assume the equations are still valid at greater than the speed of light, at least they don't blow up and have, say, like a square root of a negative number. So they seem to work pretty good. But I'm not sure that proves anything. It just means a lot of people speculate, hey, well, what if I'm already going the speed of light or bad speed of light? And then I apply these same equations. Okay, and so they call these tachyons. Tachyons, anything going faster than the speed of light. But it's more science fiction than it is science fact. It may turn out to be right, but we have no evidence of that. We just apply equations that we know are valid less than the speed of light for greater than the speed of light and say, well, that's what will happen. But we don't know that. That's a little pushing the envelope of science, crossing that boundary between science and science fiction. Well, anyways, I don't know if you caught the whole idea, but I want to emphasize then is the time between observers is going to change. That's going to open up a whole slew of problems. Because how do we get speed? How do we get momentum? How do we get kinetic energy?
By timing it.
It was all related to time. And if our understanding of time is wrong or incomplete, then our whole understanding of mechanics and the world of physics is incomplete. And so we need to kind of relook at everything along this fashion. And so just to emphasize, one of the first experiments that were done here is if you were to take the Earth and look at the upper atmosphere is hit by these cosmic rays. Now, physics beyond the scope that we've done so far, these cosmic rays come in and make small little particles, muons and pions up here, and they come racing towards the Earth really fast. Not quite the speed of light, because we'll soon see that you can't go the speed of light, but just like that electron that I got started an hour ago, it can get close to the speed of light. But they don't live very long. Their lifetime is really, really short. We make them in the laboratory, and it's so short in time that they should only go a couple of miles and then be gone. And yet they don't. They come all the way down to the surface of the Earth. We can put a container out there. We can catch them. We can measure them. Why?
Relative to that.
Did you catch this? Their time frame is different than our time frame. And so when you think, oh, they should be gone, they should not live that long, what happens? Their clock is running different. In fact, let's look closer at here. Let's go back to this. As I am moving in this train, I am moving along, or if I am this little muon up here in the atmosphere, if I am moving along, I want to emphasize, does my clock work at the same rate as your clock? And which one would run slow? Which one would run fast?
The one going to use speed of light is slow.
Yeah, notice that gamma is always greater than 1. And that means the time as measured by this inside person, the time as measured by me, is a little bit slow. And so what we like to say here is moving clocks run slow. See what I did with my, it's like, oh good, I didn't realize I went so far here. Got all these pages done here. But since gamma has got to be greater than 1, the time as viewed by the outside person has to be greater than the time as viewed by the inside person. And so a good phrase to keep in mind as you are doing the homework and after we take our optics test is to remember that moving clocks then are running slow. And that's why these guys here, when I'm on Earth, looking at them and saying, hey, I looked at my watch, you should have died by now. There is no way you should have gotten that far. And yet, the muon itself is looking at it and going, no, I'm still here, not time for me to die. You know, I live for whatever a millionth of a second is, and I'm just fine. Why? It's because they are moving. What happens to their clock? It runs slow.
So this would just be like at a constant velocity and they're not accelerating?
Yeah, now of course we analyze this mathematically with no acceleration. The same general result would come into effect if we get to general relativity, and they would still run slow. And they, bottom line though, is they do end up all the way coming down to the Earth. Now in case you think this is just untrue, let's talk about another experiment. And of course scientists did the same thing. They said, you know what, let's just build a really accurate atomic clock. It could measure things to within a couple billionth of a second. Let's just put it on an airplane and fly it around the world. Fast as we can. Put on an airplane, 500 miles an hour, go all the way around the world, and we'll land back in the tarmac. One of those clocks is moving, and the other one they left on the tarmac, not moving. The moving one should be running slow. So the two clocks, one on an airplane, one on the tarmac. Airplane takes off, flies around the Earth, lands, and they look at the clock. Guess what they find? Yep, the one on the airplane is a little bit slower in time. And so, as bizarre as it may seem, and I think it's bizarre because what are we used to? We're so used to thinking of a gamma equal to 1, what are we used to saying? The time is exactly the same. The classical story is the twin paradox. Many of you probably come across it. Your author gives you the same story. What would happen if some twins were born And as soon as the twins were born, you put one twin on a spaceship at a high rate of speed.
David DeVito.
And the other one stays here. The other one stays here on Earth. And so as life goes on here on Earth, this one on Earth will have its first birthday, second, third, fourth, and let's just say eventually they are 21. All right, and they have a big 21 birthday party, and the other twin comes landing in after going really, really fast, lands in. Twin brother goes, I can't wait to see my brother, right? I can't wait to have my 21st birthday party together. The other one is younger. Could be a lot younger. Depends how fast they go, right? And it could be as young as 1 year. And so we have one twin brother who is now 21 and another twin brother who is just turning 1. Why? Moving clocks. Moving clocks run slow. And the most important thing to realize here is this clock is not running slow because the batteries are low. Okay? This is a part of physics. This person and these people on this spaceship really think 1 year went by. They are 1 year older. Their heart beated, at some rate, however many times your heart beats in 1 year, versus somebody who's back on Earth. The electrons that orbit around the atom have slowed down. Everything has slowed down. This is not just a bad clock. This is something very new. That time is a relative quantity. And it depends what you're looking at. Which brings up a whole new set of problems. How long does it take to get to the store? As measured by whom? Right? I mean, if we all agree that we're, and maybe I should have made it simpler than that. If I shine a light beam, or if I shine or just have a car go from point A to point B, or if I set you down for a test, how much time do you have for the test? Isn't that going to depend on who's doing the observing? I mean, usually when you take a test, I put you in here, I stand in here, you got 2 hours. Person flying on the spaceship is going to look down at this class and go, they've got a different amount of time. So how do we define time now if it is always different? And it's not so simple, but we will do this. We will say that, okay, our moving clocks run slow so that we can be consistent. Let's call T sub P, okay? And let me just check the notation. Does your author use a P? He actually does this. And so I want to jump to the notation that your author uses. At this point, I've been kind of using my own notation to try and get you to see inside and outside. But he's going to call this a proper time. Some questions?
I was just going to say, do the planets move at a different enough speed to have differences in time?
Yeah. And so remember, we're not going to see anything close enough till we get to 10% the speed of light. Okay. Yeah.
So if photons don't experience time, do they have an infinite light?
Yeah. Well, until they get absorbed. But actually, and that's probably a good example of the ultimate clock here, because if you are on a photon, you are going at the speed of light. Okay? According to this, your gamma factor would go to infinity. So if you were riding along on a photon, how much time would elapse on a photon? 0, right? Because we're going to have, let's say a photon goes from that wall over to that wall. You and I would say that's probably, a photon gets about 1 foot every nanosecond. So, I don't know, is that 30 feet? So there's probably, you and I sitting in this classroom would say a photon goes from there to there, and it takes 30 nanoseconds. All right? So our time as an outside observer would be 30 nanoseconds. But if you were on that photon, your clock would be running slow. In fact, so slow that since this number goes to infinity, this number must go to 0. And so at the ultimate speed limit, there would be no flow of time. And so the photon wouldn't age. But that would kind of make sense, because remember, time would be measured in the oscillations of the wave. And so if you're traveling with the wave, there is no oscillation to that electric field. You just go along, and there's no evolvement of time, if you will. So if we could go the speed of light, you would also not be aging. But as you'll see, we had other consequences, that nothing with matter, nothing with mass, can go the speed of light. So I'm not sure this is a really good example, because I couldn't put a person or something with mass on that photon. Too bad, because then we wouldn't have time.
So you know how A equals V squared over R. So if you have two objects both moving along the circular path, just one's farther along the axis of the radius,
Right.
farther away from the center.
Circular path, acceleration,
Yeah.
not special relativity.
Okay. But
You want to ask it?
well, we can move on.
Okay, yeah.
Does position on one side of the universe compared to the other side of the universe, or one side of the galaxy compared to the other side of the galaxy? So one arm of the Milky Way versus the other arm, or near the center of the Milky Way versus one of the spiral ends.
Yeah.
Does a relativistic effect happen even if they were moving at a same V? Like if V was measured the same for both?
The two ends of the Milky Way galaxy, that's a good question. I don't think they're,
It's a bad way of putting it. Near the center, near the end.
yeah, but even they don't have a difference in speed that would be significantly noticeable. I'm pretty sure. Now, their Milky Way galaxy is pretty big. I'm not sure how fast they're going, but it's not 10% speed of light. Yeah.
Because V's a vector, does it matter which direction
No, because it's v squared. Right.
And if you have two things going opposite directions, it's half the speed of light?
Ah, a great question, right? Let's build up to that. But we will answer that here, probably before the day's done. If not this, then on Tuesday here. But the first one here, I think, is the hardest one to digest. But once we get here, then the other ones, people just kind of accept. Like, really? Okay, well, time's different. Why not this? Why not that? Why not this? And as you're going to see, something that goes 3/4 of the speed of light that way and 3/4 of the speed of light that way, when this person looks back, will not see this one going faster than the speed of light. Now, I have yet to prove that to you, but you will see that. Well, as I said, I got started here because I want to start changing my notation. I like to use the inside and the outside to get us acquainted, but that's not what your author does. Your author addresses the same question I was saying, is we are going to have difficulty saying how much time did it take for an event to occur, because whoever is doing the observing may be moving at different speeds and therefore have different times. So what we like to do here is we like to define what we call proper time. The proper time is the time you will measure with no motion. So at least we can all agree on that. We may not be measuring proper time, but at least we could say, I am measuring a non-proper time. If I was measuring proper time, I would get the same number that that person is who is measuring proper time. And so that's why we invent this, I'll call it this special location of what is proper time. So, hang on, I'll get your questions, but I've erased the picture, but of this discussion we got started with, I'm in the train moving as it goes up. One could even say it goes up and comes back down. Which one of us measured proper time?
Either. On the ground.
Okay. Well, let's see. Again, imagine me in my boxcar, and maybe if it makes it easier, let me just make sure there's no windows or no doors. And I paint a line right on the ground. That's my coordinate system. That's my 0. You paint a line on your ground. That's your 0, right? When my line crosses your line, I'm going to throw it up. That's the start of our clock, right? We start. So this object is at my 0. It's also at your 0 when I throw it up. A little bit later, it lands. I stop my watch. You stop your watch. Where is it in my coordinate system? Still at 0. How about yours? It's not 0, right? Did you notice mine didn't move? So who measured proper time here?
Depends what the frame of reference is. Is it the ground or the earth or the sun?
Well, this is my frame of reference is what am I watching? Start, stop. Okay? Where is this? Start, stop. So I would say that this is proper time. And so your author says, here is your formula. This is the way you will see it in your book when you get a chance to do the reading. And yes, I really, even though I've said it before, I really didn't expect you to have read it before you came today. Hopefully you were working on your optics and getting ready for your test here. But when you get a chance after the test to read this, you will see that your author uses a delta t for the time, and he uses a sub p for proper time. And this could be one of the most challenging parts of the chapter. What person is measuring proper time? And I'll say it again. How do we define proper time? Proper time is when there is no motion, right? And so if I have no motion, I would say, in this case, I am measuring the proper time. Now, if that wasn't bothersome for you, let's try something else here. Yeah?
Is this the idea of why Newton's laws don't apply to accelerating frame? Is that the same idea?
Oh, no. Newton's second law does not apply in an accelerating reference frame, just as they are written before we even brought up this chapter. So when you assume that the time measured by everybody is the same, you get this equation. You also can show that Newton's second law is not valid in an accelerating reference frame. So Newton knew that, and Newton said that right away. He said, if you're going to use my 3 laws of motion, you have to do them in an inertial reference frame. So no, this has nothing to do with the acceleration part. This is beyond that. This is something that Newton never knew. And nobody else knew until Einstein began to say, you know, there's something else going on here. And so he just changed the world right here by saying the times are not the same, that the times are different, and if the times are different, we have to redo F equals ma. What will we get? Fortunately, as you will see, there's this gamma factor that's going to show up, and the gamma factor is pretty close to 1 until you get to about 10% of the speed of light. So what we will say is keep using Newtonian physics until your object starts to go at a speed of 10% the speed of light. Then we have to do Newtonian mechanics. Einsteinian mechanics. And so we will go from Newtonian mechanics to Einsteinian mechanics for really fast things, because the time becomes an issue. Well, let me try this one. Let's take another look at this train. Let's change our thought process. Let's not worry about the object that I'm throwing up here. Let's just say that the train has a length L. So this is the size of this boxcar. Now, again, size of this boxcar. Let's take a look from the outside and the inside. If we are on the outside, there is this train tracks. And as it goes speeding by at some speed Vx, we just spent the first hour here saying the person on the outside and the person on the inside aren't going to measure the same time. Okay. If you accept that, then let's think about somebody making a measurement about its speed here. The person on the outside, you, person on the inside, me, would do something like this. Maybe there's a little marker on the side of the train tracks, right there. And so you stand on the side of the train tracks. And as you stand there on the side of the train tracks, what would you do? You would say, okay, if I wanted to get the speed of this boxcar, when the front edge got right here at this blue line, you would start your watch, right? You'd go, and you'd start it. And when would you stop your watch? Well, I guess when the backside got there, or some other part, some distance L. And so what you would say is there is some speed as measured by the outside person. And you say that speed would be the length of the boxcar divided by the time that the person on the outside measured. Fair enough? What about the inside person? What about me on the inside? What would I do? Well, I guess I would kind of look down here and I'd say, okay, here comes that blue line. There it is. Ready? Start. And then ready? Stop. And so I'd say, okay, this is the velocity that I see. This would be the length that I measure my boxcar divided by the time I measured. Well, if these two are going to be the same, and what did we already say about the time measured by the inside and the outside? Are they the same? So what will that say about the length of the boxcar as measured by the inside and the outside? Are they the same? And that's what I call bizarre consequence number 2. I think that's even harder to accept than this one. I mean, it was tough enough to get this one and say, okay, the times are different. But now you're telling me actual space changes? Yeah, I'm afraid I am. The size of an object is relative. So not just time is relative, size is relative. In fact, we could use the math that we did before to solve this here. I'll start off by saying, what size does the person on the outside measure compared to the inside? And since the times are different, the lengths are going to be different. Maybe I'll even start there. The length on the outside does not equal the length on the inside. And that's the second thing Einstein noticed. He goes, oh my goodness. If we're willing to say the speed of light is the same from every observer, then the time is not. And the times would be related by this equation. And if the times are related by this equation, what it means then is the length, the size of things, depends on how fast they are going. And watch what happens when you put in, and I'm going to ask this. It's not so easy, but I'm going to ask it anyways. In this experiment, which person is measuring the proper time? Now I want to emphasize, last time it was the inside person. Who's going to measure the proper time now?
So does that mean that from a photon's perspective, it leaves its origin and arrives at its destination at the same time, and its length is that entire length?
The first half, yes. The first half, there's no time.
Because time doesn't pass for the photon.
Right.
So the length would have to be the entire length of that distance that it exists.
The length would be 0.
Yeah. From its perspective?
From its perspective. From its perspective.
Photon's perspective, we're all moving in the photon.
Let me finish this and I'll answer that here. But let's come back to this question. So which one's proper time? Now remember, proper time is what? The person where the event has no motion. Okay? All right. So the inside person is not proper time. Do you see that? It's not so easy to see. And this is what you got to get acquainted with, because it's like, okay, what do we mean by proper time? And then, of course, what do we mean by proper length here? But proper time would be simply this, that the person in the boxcar, me, okay, when I start my watch, where is the little blue line? In this case, it's to my left. When I stop my watch, where's the little blue line? To my right. Was there motion of that little blue line from my reference frame? Yes. Okay. So my measurement here would be the non-proper time. Did I say that right? Yeah, I hope I said that right. Okay. Then the outside person, you, would have said, here's the blue line. And I started it right there. And then I stopped it right there. And so this would be in the proper time. And if I use the result we got earlier, and I say, okay, the person is measured from the outside, the distance is measured by the outside person, is equal to the length of the inside times gamma times delta p. And what's nice about that is then I get this nice relationship that says what length does the outside person see? What do you see? Well, it would be the length of the inside person. So the inside person would be me, right? I would stand here, let's say this is the boxcar. I would look from there to there and I'd say, okay, that's about 10 meters. Okay? And so I would say this is 10 meters, but what would you say about the boxcar? What was gamma? Greater than 1? So what would you say about it? It's a little bit smaller. And so just like we said, moving clocks run slow, here we would say moving objects contract. They look smaller. They look smaller depending on how fast you go. Now remember, this number doesn't change till you get close to the speed of light, or at least 10% the speed of light before it changes a little bit. So I doubt if you've ever looked at a car going down the freeway and go, hey, it looks small. It was a big SUV on the side and now it's a little compact when it's going down the street. Okay, but that's what's going to happen in the terms of its space, and this field is fascinating. Unfortunately, it's all close to the speed of light. So I wish I could, bring some demos out here. In fact, years ago I asked Don. I said, Don, is there any way I can show them that the time or the length change? And he thought about it for a couple days, and he goes, well, this is a meter stick, and then tell them that I took this meter stick and went running with it. Well, I don't think he really did. If he did, it's not running now. But to hopefully illustrate this is what you would see, and this is what I would see. And so the length of it is actually smaller. And some of you are already shaking your heads. I don't get it. I'll just learn it for the test. All right, okay. But maybe before today's over, I can give you some insight into this a little bit better. Yeah.
Okay. Real quick, could you tell me why the proper time was outside?
Yes. And this is going to be your challenge. And again, I wouldn't worry too much about it till after the test. But after the test, you're going to have to do some calculations. And the real key to do any of the calculations is to first find out what proper time is. So if they give you an event and they give you the non-proper time, you want to convert it into proper time. Once you know proper time, you can convert it into anybody else's time. And that's really the key. Proper time is measured from no motion. So, no motion is the key. You, being outside, are doing this. You are starting and stopping your watch when something takes place relative to this blue line. And that something happens to be the motion of the car. So, start. Stop. And there's that line. You had no motion. And that's how you want to define proper time. Proper time is no motion. But that is a hard one to define. When they give you a number, the first thing you want to ask yourself is, did they give me proper time or did they give me a non-proper time? Yeah. Yeah. Danny.
So first it's about the car and then you measure it. Secondly, if you were to take a photo of something, of a guy running with a meter stick near the speed of light, would you see the stick smaller or would something expand in the photo because it's still now?
No. The photo would show it smaller. Sure. Yeah. Yeah, so, you could start here like this. And then as you're running, it'd be like this. I guess I'd be skinnier too. I kind of like that. Right? So I'd be skinnier. Actually, some of the harder ones are, what if the meter stick was not this way, but this way?
And it shrinks along the axis of motion.
So along the axis of motion, with the x-axis, it shrinks. This one, the vertical, does not. So not only is it shorter, but calculating how much shorter is a little harder because we got to do the components. And if one component shrinks and the other one doesn't it also rotate? And actually, that's the key to the next step. Rotation is really what's going on here. And so hopefully in this last half hour we have together, I can give you a little more insight to this so you won't look quite so bizarre as you learn the material here. Yeah?
So going over time proper again, when you inside the train throws the object up, that's the point of reference is the object, right? And then when the train is traveling by, and the guy standing on the side, he looks at that blue line. The blue line is the point of reference.
Right, right. So it's a different experiment, and something different is going on. And that's why I don't want to say that the proper time would be, oh, inside or outside. That doesn't work well. What works well is when the proper time is defined as no motion between them. So in the first experiment we did, the proper time was for the person inside the boxcar. In the second one, the proper time was a different event, and therefore the proper time was outside. And again, that's one of the hardest things you will get at. Well, let's do the same thing. We have the same dilemma for lengths as we do for time. If I were to ask you how long is the car, what's our problem now? Yep, from whose point of view? Right? Who's measuring the length of the car? Because if it is somebody standing next to the car and pulling out a meter stick or a tape measure and measuring the length of the car, that would give them a different result than somebody who's flying by on a spaceship and takes a look at it, takes a picture, and they go, how big is the car? And the person flying by on the spaceship is going to see it smaller. So let's do this. Proper length. How are we going to define proper length? Let's call it LP. Right? The P for proper. How shall we define proper length? Length with no motion. Right? Okay, so looking at this, which person is measuring the proper length? The one inside, right? The one inside would look at that wall, measure across to that wall. There would be no motion of those walls, which is the length of the train, to that person. He's moving along with the walls. But it's the person on the outside who's going to see, as they go to measure the length of this, they go, here comes the train, and I don't know, maybe they shoot a laser rangefinder at it or something, but as they shoot it, they hit it here, then they hit it here, but while they do that, isn't the walls moving? Isn't the train moving towards them? And so there's motion. So the person on the outside doesn't measure proper time. So I would put in this equation that I would change it to an L equals proper length divided by gamma. And that's the equation you'll see in your book. Actually, I think your author writes it this way. Since gamma is 1 over the square root of 1 minus v squared over c squared, he takes it out of the denominator and writes it as 1 minus v squared over c squared times proper length. So whichever one you like better, I happen to like this one because this makes it very clear to me that the moving object, there's proper, the moving object will be smaller. And this makes it very clear to me that the moving object getting a different time than the stationary one, and the moving one, the proper time is going to be a smaller number than the non-proper time.
Making time L, not L.
So if I put this into here, I got 1 over, and flip it over, yeah, okay. Yeah. And so now you can see the what we call the length contraction as the thing's moving, which goes back to your question you asked a few moments ago, is what's this little photon going to see as it moves from one wall to another? From the person on the outside, from my perspective on the outside, or maybe I should say yours, because I keep calling myself on the inside, so I'll be on the photon. But you be outside of the photon. If that photon went from here to here, I would say the time it took for that photon to go across here is about 30 nanoseconds. The length it traveled is about 10 meters. Okay. What if you're on the photon? Well, as we said, and this is a little unrealistic, we haven't got that far, but anything with mass will not go to the speed of light. We haven't shown that yet, but let's just say I am, for the sake of conversation, the speed of light. Your time would stop, and there would be no time. But how far would one wall be from the other? Zero. And believe it or not, we would have, calculating its speed, 0 divided by 0. I guess we got to be a little more formal and take the limit, but we'd still get the speed of light. And so the outside person would say, how fast is the light traveling? Speed of light. Inside person would say what? Still traveling the speed of light. It went 0 distance in 0 time. And, surprisingly, it does work. It works just fine. Yeah?
So if you're looking at something going the speed of light, and the length shrinks when you're looking at it. If you're looking from the thing going the speed of light, would everything else look longer relative to the...
No, okay. And actually, hopefully my next step will help with that. But I don't know if you guys caught his question. It's a good one. Now wait a minute. What happens here? What happens if I'm moving along? When you look at me, I'm going to look smaller. Okay? Does that mean when I look at you, you look bigger? No. Because what do I see about you? I see you going this way real fast. So when I look at you, I see you shrink. So you're shrinking, from my view, but you're saying I'm shrinking. Is that possible? Is it possible that both shrink? It is. Surprisingly, it is. And here's why. See if this picture helps. One more bizarre consequence here. Let me erase this one.
It only shrink in one dimension.
Yeah, now I'm talking about only the shrinking in the direction of motion. We've only done one-dimensional motion here. We'll change it to 2 in just well, not today, and we'll expand on this. But for right now, I'm only talking about moving in the x direction and with no acceleration. Okay? Again, our first steps. All right? But let me do this for a moment. And it's actually why I brought this little metal bar out here. So we have something to look at here. Let's take a look at this metal bar here. Let's just go back and kind of everything we've learned so far for the last hour and a half. Let's put that aside for just a second. All right? Let's go back to just our Physics 121 here. Let me just put a coordinate system on here. Let me call this the x-axis. Let me call this the y-axis. Let me put this metal bar, and let me just lay the metal bar kind of along the x-axis. Okay? Now, if this metal bar is, and I'll just set it right here, just sitting there, it would probably look something like this. But on the other hand, if this metal bar was moving, let's just make it move perpendicular to the x-axis. Let's just say it moves up like that. Okay? And again, no gravity, so it's just going to be moving upward at a constant speed. Okay? So I would maybe draw a little arrowhead here. I would say V. And maybe I'll even put a little dotted line of what the ends of the meter stick might sweep out as it goes up. At some moment in time, it may be here. Okay. Still moving. Velocity V. Okay. Now, let's say it was a little different, though. I mean, I hope that makes sense to you. What if I did something just a little bit different? Let's say it's still going the speed V, but let's do this. Let's start with it so that it is not along the x-axis, but it's tilted. And so it's along the x and along the y-axis. So I'll draw this in blue. And so this metal bar may start off, well, it's going to have the same length, like this. And then let's do the same kind of experiment where we would say, let's make it move now. So we'll start it here, and we'll make it move with the same speed, okay? But it'll be at an angle now. It's still moving perpendicular to the bar, okay? And so again, I guess if I were to draw some dotted lines, it would kind of show where the ends of the metal bar kind of sweep out. In this same amount of time, instead of going up this high, it would now be here, fair enough? Now, would you agree that this metal bar wouldn't go as high as it did before? But yet it's going the same speed, isn't it? But why doesn't it go as high? Right, it has less of a y component, right? So the overall speed is still the same, it just has less of a y component. And here's Minkowski's brilliance to Einstein's work. He said, Einstein, do you realize what you have discovered? You have really just shown that space and time are not separate, but the motion of an object changes its time and changes its length. In other words, Einstein, we don't live in a three-dimensional world, x, y, and z. Time is connected to the x and y motion in this way. Let me draw a new picture here. Let me draw, and I'll do the axis maybe in the same color tones here. Let me call this the x-axis, and let me call this the time axis. Okay, see the analogy? I'm going to treat time as if it is a fourth dimension. Not x, y, and z, but x, y, z, and t. Look what happens. What if I were to take this rod and place it right here? Just like in this picture, if I were to place this rod right there and not move it in the x-axis, there it is, not moving in the x-axis, what is it doing right now? It's moving through time, just like you and I. We are all flowing through time. Tick, 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 tick. And Michelson begins to notice that if you were to take this object and say, it is moving through time at the speed of light, terrible word, at the speed of the universe, that is what nature does. But on the other hand, if you were to take this object and move it horizontally, the picture would now change. Oh, let me finish the picture here. So if you did not give it a horizontal speed, what would happen is that metal rod would have progressed in time. Let's just say 1 second. But on the other hand, if this metal rod, like this one over here, has a horizontal speed, its total speed doesn't change. It is still going at the speed of light, and 1 second later, if you will, and I got to be careful about that 1 second, it would be here. But what I want you to see is just like here is the metal bar as far up on the x-axis, I'm sorry, on the vertical axis, which is time, as this one is before. And this right here is our time dilation. Do you see that? see if this helps, right? Back here, what was happening here is you said an object that keeps traveling the same speed but uses some of its speed in the x direction means it doesn't travel as fast in the vertical direction. And that's what I'm trying to say here. This will hopefully give us a better understanding. Time is part of our coordinate system like x, y, and z, but unfortunately us humans were too stupid to realize that.
So mechanics should have a time vector.
Oh yes, and it does in Einsteinian mechanics. It is a four-dimensional problem here. And the whole reason we have a time dilation hopefully isn't as big of a surprise as it was an hour ago. It's because what's happening, instead of the object going at full speed in the vertical direction, it now has the same full speed but off at an angle, and it doesn't advance as far in time. And it doesn't advance as far in time because we've used some of our speed to move over in space. And so space and time are connected together. And in fact, we will stop calling it space and time. We'll call it spacetime. And just get rid of the and word right there. They are connected together. You can't change one without changing the other. In the same way, you can't change x and y without changing x and t. They are interconnected together. Yeah.
I'm a little confused with the picture. On the left, like when you rotate it, I mean, our axis is like a two-dimensional space, so like, I mean, the bar is actually rotated. Like, what do we mean by when we rotate the bar and axis?
Oh, I am so glad you asked that.
That doesn't necessarily
Oh.
rotate in space.
Oh, you just asked more than you are ready for. Okay, you ready? Okay. But I'll start with this one, because this is how I started this lecture. I showed you what I called bizarre consequence number one. That is the time from the moving object is less than the time from the stationary object. And what I meant by stationary object is moving in space. Okay? But let's look at the other part. You said a rotation. Okay, let's look at this rotation. Let's look at it down here. Or I guess I could look at it here. I don't care where you want to look at it. Maybe I will change the colors here. But when I make this rotation, as you said, this fit fine in your head. You said the endpoints were rotated so that this endpoint was a little bit lower on the y-axis than this endpoint, and that then it had an x component and a y component. Let's look at those for a moment. Let's look at the x component. If I were to take this rod and draw its x component, what would you say about the x component compared to the length of the rod? It's smaller. What did we just get saying about something that is moving? What happens to it? It shrinks. You see somebody standing on the outside. You standing on the outside, you call it a shrinking, but what really has happened is that rod has less distance on the x-axis. Where is the rest of the distance? On the time axis. Oh, and this is going to be even weirder. So bizarre consequence number 3. And this was my goal today, to show you 3 bizarre consequences. Let me just remind you of the first 2 easy ones. The time is dilated, and 2, the length is contracted. What is this one telling me? Now that I have rotated it in the time axis. And again, it's difficult for me to show you because I can't rotate this in the time axis. But when this thing starts moving, the whole reason it looks shorter, the whole reason it goes from here to here is because this has rotated, and I only see this much on the x-axis.
The back is in the past.
This is at a different time location than this. Now, what does that mean? Well, that means if the meter stick was sitting here and not moving, and 2 firecrackers went off, at the same time. But it was moving. Would those firecrackers be the same time anymore? No. And so the third bizarre consequence is what we call simultaneity. It's gone. Those firecrackers, one person is going to say, the person who's looking at it this way is going to say, when did those firecrackers go off? And they're going to say, same time. What's another person going to say? Different times. And the whole idea of events occurring at the same time completely goes away. And Don, I think, has made a pretty good video to illustrate this as the spaceship goes along, and he uses these pulses of light to try to get it. I like this little diagram because this diagram shows what's really going on is we don't have space and time, we have space-time. And when you mess with space, you mess with time. And if something looked like they went off at the same moment, when they had zero speed to one person, so if the person is sitting on this metal bar, they're going to look at these firecrackers and go, yep, they went off at the same time. But somebody outside is going to say, oh no, you are so messed up. That one went off first before that one. And the whole event of what occurred first is really, really hard to define because our time and space are interwoven together. Yeah?
So because we're on Earth, like moving really fast through space, are we not going the full speed of time?
Okay, so fair enough here. You would argue here then that, you know, what I guess what I'm going to say is time then becomes relative. But I don't think I would kind of answer it the way you just said it. I would answer it in the sense of how is my time relative to somebody else's time?
There's a maximum like limit of time, speed of time.
Well,
Because if it goes out of time, then it goes into
okay, so let's say I'm in this giant spaceship traveling through space. As I go along here, and everybody who's in my spaceship, they're not moving relative to me. So whatever the rate that time progresses relative to the other people in the spaceship is all the same. So we do the same thing. We get up in the morning, we do our chores, we do whatever we're required to do by NASA and blah, 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 blah. We do our exercises. And we don't notice anything unique or different until we come to another person or another place where there's been some relative speeds between them. Right. Now, let's go back to this photon, wall to wall. What did we say? How far is it when you are on the photon? It's all crunched together, right? Meaning what? Meaning if you're that photon, you can't look forward and say, how far to the library, right? Because where is the library? Okay, it's right there, right? You can't look behind you and say, where was the humanities building? Why not? It's crunched together. Okay. So what if I stand here in the room and I don't move X, Y, or Z? I claim that I am moving at the speed of light on what direction? Time. And so what would happen to my time axis? So can I look and say, there's tomorrow? Can I see tomorrow? No. I can't see yesterday. This is why we as humans have a hard time understanding that time is just like space. We are so busy going the speed of light on the time axis, and it has shrunk down, and it looks totally different to us than the x-axis. But just like a photon going here could not look forward and say, there's the library, I cannot stand here, you cannot stand here and look forward and say, oh, there is the tomorrow. I don't see that. Well, before I run out of too much time here, let's go through this little animation here. Here is the first page, if you will. Here is this experiment, if you will, of simultaneity. I can't say that. Simultaneity, where what happens is we burn these at the same moment. And you can see that there's going to be a flash of light coming from this one and a flash of light coming from that one. And the whole reason this little recorder here says they occurred at the same moment was because the little flashes of light hit it at the same moment. They're the same distance away, and they're traveling the speed of light, and they come and they hit it at the same moment. So this person, or this instrument, is going to say those two burned at the same moment. But if I send a spaceship racing on by, and I have another data recorder right here, and these things fire when the data recorder hits right there, watch what happens with that one. Did that data recorder say they occurred at the same time? Mm-mm. That data recorder has clearly picked up the flash of light from this one before it picked up the flash of light of that one. So one data recorder, this one, not moving, is going to say they happened at the same time. This one is going to say, no, this one occurred first. I saw the flash first. It was later on that I saw the flash from the other one. And so you will get a slightly different result. Well, maybe I'll kind of leave it there and say, okay, so there is our three bizarre consequences. So, maybe that's a good place to stop. Yeah, if I get started in the next topic, yeah. All right, so anyways, so good first step, very different. Get ready for the test, and I guess worry about the rest of this after Thursday.